So my name is Stephen Elliman. I'm super senior here, and I am double major minor computer science at econ, minor anthro. And
I'm Jeremiah, and I am an EECS junior transfer, so I just got here, and I'm into blockchain stuff. And yeah.
Okay.
So you take it away. Go ahead.
Great. Let's get started. So it's Privacy Coins deep dive. So with our today's agenda, it's going to be first like an overview, and then afterwards talk about CoinJoin, Dash, Monero, and then Zcash. And the last three, Jeremy will cover. So first off, let's just overview. Why do we want privacy? So as individuals, we of course want to keep our history of transactions secret. And the reason why is like who you interact with, who you transact with, and how much these can be used against you. This is valuable information. So it also, if people know who you're interacting with, it can kind of lead to inferences about your consumption patterns. Finally, a kind of social graph of your trust relationships can really be inferred, which is a little dangerous. Second thing is more of an architectural question, which is to keep currency fungible. So fungibility is when, let's say, $1 is interchangeable with another dollar, or one Bitcoin is interchangeable with another Bitcoin. And the problem is, by default, this is not true with blockchain-based cryptocurrencies, that fungibility is not the default. And the reason why is that for each Bitcoin, there is a full history of transactions that's wrapped up with it. And what that means is that the value of one Bitcoin for one person might be different from another. And this really impacts the stability and usefulness of a currency. So the reason why the kind of default blockchain-based currencies are not fungible, so imagine a scenario in which like Bitcoin X implicates you in criminal activity, and a Bitcoin Y does not. For you, for let's say criminal associates, for the police, Bitcoin X might be more valuable because it can be used against you, or can, you want to save it for yourself and not be implicated. But for the rest of the community, Bitcoin Y is a lot more valuable. And the reason why is they don't want to be implicated with your business. So what it means is that because you have this history of transaction that's wrapped up with the actual currency that you're talking about, it's not one-to-one. It's not fungible. And another example, kind of non-fungibility is, there's a thriving kind of collector's economy because celebrity and history does impact the value of arbitrary goods. And so again, as a currency, that's problematic. So the whole point of money is to lower transaction costs, and that's where we use it. So if we had to have an economy in which, let's say, a new car had to be bought with corn, or let's say college tuition exchanged with chickens, guess what? Modern economy would not work. So greater fungibility means lower transaction costs as a currency, and consequently a much better, more stable currency. So what it means is that the less information you offer about individual let's say Bitcoin, and like more privacy you offer, is kind of roughly proportional to the amount of fungibility you have as a currency. And that's important again as more of an architectural, at a more architectural and economic level. So what we're going to do is kind of walk through options, starting with mainstream and then moving to more privacy-centric currencies. And this is going to kind of start with the open defaults to closed defaults, of starting with Bitcoin, Ethereum, mainly Bitcoin, and then moving to Dash, Monero, etc. This also kind of moves from least to most fungible. And the reason why, again, is because there's kind of a proportional relationship, a roughly proportional relationship between privacy and fungibility. And then finally, this is kind of roughly chronological as well, because actually, I'm going to cover this next slide, never mind. So important note, all the kind of privacy concepts that we discuss here do not apply to side information or side channels like networking information. So all of that, like let's say having IP trace, whatever, that is not discussed. It's not really within scope, because you need to cover your tracks elsewhere. You need to use anonymity networks like Tor in order to really account for those side channels. So beyond the scope of this lecture. Okay, so what is the default privacy of Bitcoin? And the answer is not much. And the reason why is because the incentive system outlined by the system is that miners must be able to confirm a transaction's validity. The entire world has to be able to confirm its validity. And what that means is if that transaction information was encrypted, how would they do that? And again, that requires very sophisticated cryptographic primitives in order to do that. And that's really where things like Zcash come in. So as the default information in a transaction of Bitcoin is the sender address, receiver address, and amount. And what this means is because transactions are tied to an address and not an identity, it is somewhat anonymous, provided you have security through obscurity. What that means is provided you don't link that address, provided you can't link that address to, let's say, a receiver or sender, then you're okay. But if information is leaked and that there's a tie is made, what that really means is that any other transaction that uses those addresses has been compromised. That an identity can be tied to it. It's no longer anonymous. And again, that's problems because of fungibility, among other things. A naive solution to this is every transaction make a new address. But the problem with this, actually first, this does superficially solve the problem. The problem is like there are other issues now that come up, which is first off, without HD wallets, this is like kind of time consuming. In fact, it is time consuming. And then second issue is that for mutually trustful actors who are familiar with each other's unique addresses and are trusting each other, it can be very useful to have that identifier. It's almost a kind of can be used as a unique identifier. And without that, there's a little bit more of a transaction cost. And then finally, the most important thing is that it can be broken with taint analysis. And taint analysis is kind of like probabilistic tracking of first being able to make up this transaction graph of sender, receiver, and the amount of Bitcoin that's being transacted, and then following through of making a directed graph with time and between time, address, and the amount, and being able to, in some sense, construct relationships. The taint in taint analysis is when you, rather than using the amounts, you use kind of the percentage of the amounts of contributions and distribution for the receivers and senders, and through that, have a better idea of the influence that they kind of imparted on that transaction. So a solution to this is to obscure the transaction via aggregation. Of imagining there are two exchanges that are taking place simultaneously, and both parties benefit from heightened security. Heightened privacy. So what that means is that why don't they aggregate together? And that's precisely what what is done with like CoinJoin, in which what basically if they join transactions together, you are able to increase the anonymity set that kind of collectively obscures these relationships between inputs and outputs. And this can offer a lot of positive externalities for the kind of privacy of the entire community, which is good. So that is CoinJoin. And CoinJoin is implemented most frequently on a centralized server, but there are some distributed protocols. But the downside of centralized is that it does require kind of a trust anchor to a certain. It does require a trust anchor, but the reason why it's utilized is much cheaper. It's cheaper and it's easier to implement. The pros also, as well, is that this protocol is trustless because of how Bitcoin is constructed, in that all transactions and all involvement have to be signed. It means the end transaction, the actual redistribution, can be checked and signed by everyone, has to be signed by everyone. So it means that there's a way of verifying that this transaction, basically nobody's being cheated, which is very important for it to be useful. The con, though, is that simplest implementation, only insiders, only participants of the CoinJoin protocol will be privy to the inputs and outputs and how they relate to each other. So for the insiders, it doesn't really help with privacy, but for the outsiders, it's a pretty good method for having this more obscurity. Another downside is susceptible to two kinds of DOS attacks. First off, if you're a participant, you can refuse to sign the transaction. And in doing so, even if it was a valid transaction, you will stop it from occurring. The second way of also kind of DOSing it is if you spend the account, if basically the address that you provided initially, you spend the account, it means that when a final check is run, that you actually have what you say you have, it will fail. And as a consequence, the entire transaction will stop. The third issue is that there's limited liquidity, and that's hard to often get the timing right between when someone needs the service and when someone actually can offer Bitcoin readily to enable this transaction. So one way of getting around that is with CoinJoin, Join Market rather, and facilitate CoinJoin. And what Join Market does is offering the incentives for that kind of extra participants and that extra liquidity. So they have a maker-taker concept in which makers allow their extra Bitcoin to be used for a fee by a taker. And in theory, it can offer much greater liquidity at larger anonymity sets for a low cost. In practice, it's slightly different in that, so it does offer significantly more liquidity, which is great. It also, in terms of costs, it does fall mostly on the takers rather than makers, because the takers, the people who want this liquidity, if the people who want more privacy, also have to expend, are responsible for the cost of the makers, which makes sense to a certain extent. The thing that kind of diverges from reality is that they're actually still really low anonymity sets, and that you would expect that given this liquidity, given the cost, that people would be, really increasing anonymity sets to something like 10, 20, 50, 100 people, so to really maximize privacy. But really, on average, it's 2 to 4. The set is only 2 to 4 others. So it means that there's a kind of, it's not, people are still probably a little bit, they're not secure, not private. Yes?
What does the anonymity set mean?
Sure. Oh, I'm sorry. So the anonymity set is like so when you have a transaction, there are a limited number of kind of receivers and senders, right? So the anonymity set is trying to increase that value of the number of participants involved so that it's harder to match inputs to outputs. And that's very important, again, for this question of anonymity, and the question of kind of trying to break the relationship between those two. Because if you can make a relationship between those two things, of inputs and outputs, of senders and receivers, it means that techniques like taint analysis can basically be used, and privacy can be, identity can be inferred through your relationships. Right. Yes?
Why would any user even want to have to trust in solutions like this? Why wouldn't you just instantly want to have, use a fully anonymous wallet, for example? Like, why would I want to be disclosing any address that could be linked back to me ever?
It used to be the only way to do it, basically.
Yeah, so
I could just keep giving you a stream of freshly generated addresses, right? That I can continue to generate, let's say from a seed, right?
Well, that's what you were talking about earlier.
So,
with the HTML
the problem is that even with that, with addresses, if you ever need to re-aggregate money, let's say, there's still relationships for 20. Let's say you split up a bunch of different transactions among different addresses, right? Yeah. What happens is if you ever want to make a large purchase, all of those separate addresses somehow need to be used together in order to make a large purchase. So the problem is that if you have this transaction graph and all these relationships, you will be able to see how they're related to each other anyways. So in some sense, what CoinJoin is trying to do instead is, yes?
Okay, so certainly I could agree with that. That assumes that there's this whole necessity to join.
Mm-hmm. Right. Oh no. So that's okay. So
to join transactions
that doesn't say it's. So the only reason why CoinJoin is used is to try to break the relationship between the inputs and outputs, rather than the relationship. What you were mentioning before is the relationship between, in some sense, the addresses and. Oh, sorry.
Like identity and address.
Yes. Yes. Exactly. But what this is trying to deal with is relationships instead. Of saying that in the case of what you mentioned, having many different addresses, let's say if that party wanted to re-aggregate their funds, that would be seen without CoinJoin, let's say. But if they were able to increase their anonymity set by paying a bunch of takers, let's say, then they're able to obscure the fact that they're trying to re-aggregate their funds. Okay. Does that make sense?
Yeah.
I'm sorry. Yeah.
I'm trying to understand why this problem arises, and it seems like it's because at least some of these protocols you have to spend all your coin, and then that creates a connection between all your previous coins.
Yeah, go for it.
I think that is sort of like the source of it. That in Bitcoin you have the UTXO model, which is basically that anytime you make a transaction, you have to completely spend the coins that you have. And so if someone sends you 5 Bitcoin and you want to send someone else 1, you can't just send 1. You have to send 1 to them and 4 back to yourself. And so you always end up with these smaller change amounts. And the problem is, even if you used separate addresses, so every time you made a new address to send that change to, at some point you're going to spend some of that change, and then all of them get linked back together. And so you need some way to break those links so that you can separate out different transactions from each other.
So do you know why all the coins have to be spent at the same time?
Basically, it was just that Bitcoin was designed that way because it made it easier to reason about. I'm not a big fan of the UTXO model personally. I like the account-based model of Ethereum where you just say how many you want to spend and then your account is lowered by that much. But in Bitcoin, the UTXO model does create some problems in that way.
Yeah. My understanding is so that because of the ability of having multiple inputs and outputs and the fan out that can be caused by that, it limits the amount of looking into past history you have to do to find out if the coins are spent or not, something like that.
I guess that is true. Yeah,
I see that.
You can trace back the coins to where they came from.
Yeah, you don't have to search infinitely far back.
Right, just back to their Coinbase transaction. That is true. But yeah, so because of the UTXO model, though, that's why these things like CoinJoin are basically just a way of saying, I have a bunch of UTXOs and a bunch of other people also do, and we want to get new ones that aren't directly connected to the ones we already have. And so we all put ours together, and we all get a bunch of new ones out, and there's no way to say, these were my inputs, but which of the outputs belong to, the identity that had the inputs. It's a lot harder to tell. But, as he was saying with the stuff about the 2 to 4 anonymity set, it's really hard to build very large CoinJoin transactions that give you like say if everyone in this room wanted to mix all of our money together so that no one could know whose money was whose, except for us, you can't do that on Bitcoin. Like, it would be a very large transaction that
Yeah.
just wouldn't fit, in a block, really.
Also, there are just like so many different transaction costs associated
Right.
with making a very large coin join. Like if someone, for instance, did just not sign a
Right.
large
It's a really
transaction,
bad
it means
coordination problem.
everyone fails. It fails for everyone. So
Right.
there are a lot of issues, and that's kind of where the other solutions come in, is because coin join is insufficient. So now passing it over to Jeremy to discuss Dash.
Yeah.
There we go.
So Dash is basically the ideas of CoinJoin, but you build a network. And so they have these things in Dash called masternodes, which are basically just servers. And there are about 4,000 of them, I think, right now. And because of how Dash does, like the total number of coins is capped, and you need 1,000 Dash to run one of these servers, there can only be like 4,500 of them in total. And so it's a very limited number, but the idea is each masternode acts as a facilitator for CoinJoin. And so you send basically a transaction or a message to a masternode saying, I want to participate in a CoinJoin. The masternode then waits for 2 other people to send a similar transaction or message saying, we also want to participate in a CoinJoin. And then once there's 3, the masternode can go, okay, this can be a group of 3 people who mix their coins together. And so they do this, and the idea is that the wallet software for Dash will continuously run your coins through these mixes so that it runs through multiple hops of this kind of thing. So at each step, you're only getting, you're only mixing your coins with 2 other people's coins. But if you run it through multiple steps, then at the end of it, it's very hard to track, where they went, where they came from originally. And so I have a graph here that I made this morning, which is not great, but it sort of brings across the idea that, can you guys actually read what it says in any of that?
Yeah.
A little bit. Go ahead.
What did you mean by very hard to track?
So, right, the idea is that. Is the laser pointer? Yeah. Okay. So, like the middle circle on the bottom part is labeled Bob, and then the sort of circle here is Robert, right? So it's like that's still Bob, really, but he exchanged some coins for different coins, and it's impossible for someone looking at this to know which of the 3 inputs matches which of the 3 outputs, right? But it's still like it's 1 of 3 if you just guess, so it's not that much security. But if Robert, right, who's really Bob, goes through another masternode and he becomes Bobby, right? It's like, okay, now you've got, Bobby, Francis, and David are like 3 outputs from that masternode. And the idea is if you do this like 8 levels deep, at every level you're multiplying the total number of possible inputs that are leading to that output by 3. And so I didn't draw, all of them because that would have taken a very long time. But the idea is that by going through multiple layers of what is basically just a 3-party coin join, the total, like what they call the anonymity set, is pretty large. There are some problems with this, which is that, like in this diagram here, in the first mixing, right, Robert ends up going through a second mixing, but Charles and Alicia, who are really Charlie and Alice, neither of them mix their coins with anything. And so there aren't other inputs that are being mixed into the possibilities, right? So it's, there are really like 5 total inputs on this slide, where you would hope that after 2 steps there would be 9. And so the problem is if other people don't mix their coins as much as you mix yours, then you don't actually get the 3 to the n anonymity that you think you're getting, which is what I think I've got on this slide.
Sure.
So, yeah.
Just in the case of, these obscuring mechanisms and techniques, what prevents a user who wants to track this information from obtaining the aerial view in this regard?
Right. So, in some sense, nothing, right? Because if you were, say, the NSA and you could observe all of these servers doing all of this communication, you could probably track that, oh, this user submitted a transaction to this masternode, and then the same IP address submitted another transaction to another masternode, and you could probably trace it through like that. But we are sort of assuming that we don't have a sort of bird's eye view of the network itself, because if you do have that, then a lot of these processes don't work that well. Zcash, I think, actually would still be all right in that case. But yeah, for something like Dash, where you have to interact with a bunch of servers, if you could watch someone interacting with each server, you could pretty easily conclude that, they are the one entity that goes through all of those servers. So good question, actually. Thank you for that. So yeah, so here we got a little bit of like a breakdown of how private send is. Private send is what they call this mechanism in Dash. Yeah.
Do all people have to contribute the same amount for mixing?
Yes. Also a good question. Thank you for that. So in CoinJoin, you can have different amounts, and that leads to a problem that we didn't put on one of the slides called CoinJoin Sudoku. That because if I put in 10 Bitcoin, I have to get out 10 Bitcoin. The outputs might not be exactly 10, but they will add up to 10. Like the ones that are my outputs will add up to 10. And so if you have a bunch of people putting in a bunch of transactions and then getting a bunch out, you can take what they call a partition of the output transactions, and you can check that their sums equal the values of the input transactions and find which ones match to which. And so in Dash, they try to get around that by saying, okay, each of these mixings, it's either 10 dash, it's 1 dash, or it's 0.1 dash, I think. And so the idea is that, you know, in these three-party mixing, you know, steps, Alice, Bob, and Charlie, each of them is putting in 1 dash. None of them have different amounts because that would really complicate how to actually implement that in a secure way. So yeah, any other questions about stuff I haven't talked about? Okay. So yeah, you only have to trust that in a graph like this, if you go through, you know, 10 or 20, I think the standard is like 8 steps, you have to assume or hope that at least one of these masternodes isn't keeping a record because, you know, M1, the first masternode, it can see who it connected to who, right? Who, you know, Bob gave coins and then it gave those coins to some other account which is still owned by Bob. And then that masternode knows who it gave those coins to. And if every masternode along the chain knew and kept track and like shared that information with each other, then they would be able to know where the inputs and the outputs go. And so you have to assume that at least one of the masternodes in the chain is not doing that for you to have the security that you're hoping for. And the idea, you know, the theory in Dash is that it's really expensive to run one of these masternodes, right? It's currently $300,000. You have to like buy 1,000 Dash, then you have to like stake it to be able to run the masternode. And then I don't know that they have any, like there's no way to detect if you are keeping track of like what transactions are going through your node. So you're not really putting that money at risk if you're snooping on people, but it does cost a lot of money to do. And so the idea is that if you wanted to attack the network and be able to observe people's transactions, you'd have to run a very large percentage of the 4,000 masternodes to be able to, you know, have the average transaction going entirely through nodes that you run. And so that would be very expensive to do, and hypothetically, no one would do that. But that's not a very real assumption. So the idea is, yeah, it's, in each step, you're only actually gaining 2 sort of ambiguity values, right? That like, when you get an output from a masternode, you got a transaction output, and it came from one of the 3 people who put in money, and no one can prove that it was, you know, the input that you provided. It could have been one of the other ones. But after going through a bunch of stages of this, the total possibility of inputs that could have led to your coins that you have now, in theory, is very large. And the idea is if you run this through enough steps, it ends up being larger than the total number of actual transactions that exist on, you know, the network, and so it could be any of them. But in reality, it doesn't work that way, because if other people don't wash their coins as much as you are, or if other people, say if someone sends their coins through a bunch of masternodes, but then they send it back to the original address that they used to start the chain, well then you can you know that their coins went back to where they started, and you can basically remove them from all of the possibilities. And that's a general problem with basically all of these except for Zcash. Which, yeah. Any questions? All right. Feel free to like stop me if I am going too fast or being confusing, because it's only going to get worse from here. Okay, so right. Here, there be crypto. So Dash was all right to explain. I don't know that I did a great job of explaining it, except to try to say that it's just mixing coins together and then doing that through multiple steps. But Monero is basically, you want to do the same kind of, go ahead.
Is that to say that like between Dash and Joincoin, is it just that Dash is doing this sort of mixing step more times?
Right, exactly. That's basically, I think I wasn't there, I don't know, but I think the design philosophy of Dash is basically, we want to have servers which help people do CoinJoin and just make it really easy, and then they just do it a bunch of times, and then you can get all the benefits of CoinJoin without all of the costs of, either arranging it yourself or using one of these services that is going to charge a high fee. You can just have it be part of the network itself. And then there are other reasons for the master nodes that we're not getting into that are useful for like fast transactions. But for the anonymity, they've just basically said, CoinJoin works well enough, let's just build a system that relies on that. Monero is basically, you want the properties of CoinJoin that you create ambiguity of like, I have coins, where did they come from? Well, they came from one of these inputs, but you don't know which one, right? And Monero basically says, well, what if you could do that without having a server that you have to send the coin, or send a transaction to, which then mixes them up. If instead you create all the outputs where you say, okay, I want to have these coins when I'm done with this transaction, right? These are the outputs I'm going to have. And then you're going to say, I have my real input, and I have a bunch of fake inputs from other people that they are real inputs, they are real coins that are on the network, but I'm not actually going to use them in my transaction because I don't have the authority to actually use those. But the idea is that you don't need to ask those people to sign the transaction with you. You create a transaction that says, here are the possible inputs, one of which is the real input, and then here are the actual outputs. And the way you do that is with some really kind of messy crypto, which is all of that. So yeah, the basic idea of Monero is you make, through these cryptographic properties, you make a transaction that says, here are a set of inputs, and here are a set of outputs. One of these inputs matches this set of outputs. And I can prove that, and I can sign it, and I can authorize that the input that is leading to these outputs is signing off on this transaction, and all of the numbers add up, and everything's fine. And no one verifying the transaction has to know which of the inputs is the real one. But to do that, we have to go through some crypto. So this is the part where anyone should feel free to ask questions a lot, because this stuff is confusing and I don't fully understand it, but I can try to talk through it a little bit. So first step is you have something called a ring signature, which is the basic part of saying, I have a public key and a private key. I can sign for my public key, and it can be verified, in all the usual standard ways. Is everyone here vaguely familiar with signing as a concept? Okay, feel free to say you're not. Okay, so you do that. The idea of a ring signature is you can take a bunch of other people's public keys, and you can create a signature using all of their public keys and your public key and your private key. And anyone else can verify that this signature was created by someone in the group of public keys, that someone in that set of public keys has one of the associated private keys, but they can't figure out which one it was. And that's very useful in Monero because that's what allows you to say, one of these transactions is owned by me and I am authorizing this resulting transaction to actually happen. But there's no way to check which of the input transactions is the one actually signing off on it. And then we have traceable ring signatures, which is the same idea, but if there are two different messages which are signed by the same public key, even if they use different fake public key groups, if it's the same private key that's actually signing them, you can compare the two transactions and you can extract which public key it is. Yeah?
I have a question about ring signatures.
Okay.
So,
give me my water.
If you have some transaction, transaction output that you're assigning so you can spend it,
right.
There's only a limited number. That transaction output can only be spent by, let's say, one private key holder.
Right.
So in that case, how do ring signatures provide any plausible deniability? It's like, okay, well, A, B, and C might have signed this, but we all know that this transaction output is only spendable by C, so...
Right, well, that's the idea, is that, I get what you're asking, I don't really know how to... So that comes into a later part of this where that is a problem, that if you can figure out, I create a transaction, and I say, I include one of his transactions and your transactions that aren't spent yet on the network. And I say, okay, we've got the inputs of my real transaction that I have from somewhere else, your real transaction, his real transaction, and then I sign it, and it came from one of the three of us. If sometime later you create your own transaction and you just directly sign, well, then it's well, you signed that one, you couldn't have signed this one.
Yeah.
And so now it's well, you didn't sign this one, so maybe it was one of the two of us.
Yeah, and then also, how do you know what was actually spent, right? If you have these three inputs and
right.
you're only actually spending one of them, but you're signing as if
Right.
it could have been all three of them.
That is a problem that will, let's see.
I can
So
wait.
that's the commitment schemes and the confidential transactions part where you hide the value of the transactions. In the first iteration of Monero, they made it so that you had to match up the amounts of the transactions, and I didn't read much about that because it's no longer how it works. But from what I understand, it was a lot more complicated to make it work then. Whereas now they have these things called confidential transactions that allow you to hide the amounts of the inputs and the outputs, so that you don't your transaction is for 5 Monero, mine's for 10, and his is for 3. I can have an output of 10 or whatever, and it doesn't matter that it doesn't match the fake inputs because you can't actually see what the values are, and that's a later complication. But thank you for asking that, because that is the problem with this is there really isn't a good way to get how the system could possibly work when you are trying to make it secure, that you can't sign for other people and you can't sign a transaction that creates value out of nothing, right? The values have to add up, the signatures have to be valid, and the fact that it works is kind of magic.
So are they using UTXO or is it account-based?
It's UTXO. So each UTXO has a public and a private key and can only be signed for once, basically, and so you have to spend it entirely. And this is something where it wouldn't work very well in an account-based model because you still have to treat it like UTXO. You'd have to spend everything out of the account at once. Otherwise, the next time you tried to spend, it would break all of your previous transactions. It would break the anonymity on them. So so traceable ring signatures are basically that idea that if you have 2 transactions signed by the same person, then you can check them against each other and you can figure out which public key actually signed both of them. And that would allow you to detect that this UTXO was actually spent already. And so this person is trying to double spend. And then it's sort of the idea that if you try to double spend, we'll catch you and we won't allow it, and we'll de-anonymize your old transaction. But I don't think that gets put into practice much because most people don't try to do it. Okay, so commitment schemes are the other part that you need, which eventually builds to how you hide the value of each transaction. So a commitment scheme is a way to commit to a value without revealing it when you're doing the committing, right? So I want to, the classic example is I want to make a bet, right? So I'm going to say what the score of the end of the game is going to be. I'm going to write it down, and I'm going to hand it off, and we're not going to open that until the game is over, and then we're going to open it. But we have to find some cryptographic way to do this because it's all done over the internet. And so the easiest construction for this kind of thing is a hash function, where you take, everybody know what a hash function is? Okay, if not, feel free to ask questions. So you take a hash of the thing you're committing to and some random value, and the idea is that because of properties of hash functions, if you just reveal the value and the random secret thing, then anyone can check that, oh yeah, the hash of that matches what you gave me in the first place, and there's no way to figure out, if you just have the hash, you can't break it open and figure out what the secret value was because of a thing called preimage resistance. And you also, if I give you a hash of some value and some secret, I can't then go, my bet is wrong, so I'm going to change the values, and it'll still match the hash. You can't do that because of a thing called second preimage resistance, that basically you can't change values in a hash and end up with the same output, or at least it's really, really hard to do. So we've got that, and that brings us to additively homomorphic commitment schemes, which is the same idea, but you have this property that if you have 2 commitment schemes to numbers, and you add them together, then
so, what's the point of the whole commitment schemes again? Why
so
do you need the hashes?
the hash, that's just an example of the easiest construction of a commitment scheme, of a way to get someone to write down what a value is without anyone else knowing what it is, so that they can't change it later, and you can be assured that once they release what the value is, that was the value they gave you in the first place. But also the person getting the commitment can't see what it is until the reveal stage. So it's just a way to commit to a piece of information without revealing what it is. And you need that in Monero so that you can commit to the values of transactions without revealing what those values are. So you do that with additively homomorphic commitment schemes, which basically just means that if you have 2 commitment schemes to numbers and you add if you have a commitment scheme where a commitment to a number is some value, right? It's a mathematical value. You can add those values together and that is equal to what you would get if you committed to the sum of the two values in the first place. And how you do that is cryptography. There's a thing called the Pedersen Commitment scheme, which I think the original one was based on large groups based around large primes. But in the context of Monero, it's all based on elliptic curves because the group theory is all the same. And the other key property of them is that if you have a commitment to some value, you can check that it's equal to some other value. And you need that so that you can check if this commitment is equal to 0, or equal to the commitment for 0. Yeah.
Can't you just then like generate a bunch of, like, can't you then brute force the commitments by seeing, like, generating a bunch of commitments and checking them against that?
You can if you know the secret value. So like in the other example, you had like the value and then the secret. The idea is that if you add two commitments, I didn't put that in on this slide, but if you actually commit to A, it'd be committing to A plus a secret value for A, and it'd be a commitment to B plus a secret value to B. And what you would find is that the secret value in the commitment to A plus B would be the addition of those two secret values. And so there's no way for someone else to generate your commitment and figure out what the internal values are unless they also know what that secret is.
Okay, so it's possible to prove that like a commitment to 0 is a commitment to 0 when you know that secret value.
Right, and so that's the idea, is that you can... Actually, I don't know if that is the case. I think for a commitment to 0, you might be able to check that, because the miners have to check that. Just, it's a little late into it, but fair warning that I'm not an expert in this stuff. I've just read enough about it over the course of the last week or two to build this presentation, and then I'm going to read a bunch more with you guys when we actually get to the reading part. But yeah, additively homomorphic commitment schemes are a really interesting thing, and they're probably the main thing to take away from Monero, actually, because they're useful in Zcash and in a thing called Mimblewimble, which I need to read more about. But yeah, basically, you can create a commitment to a value, and then you can add them together, and you can check that, in this case, you can check that the resulting commitment is a commitment to 0, which, you use commitment schemes on transaction amounts, and then the miner can check that the input transaction commitments, when you add them together, they equal the output transactions by adding some and then negating the other side, adding them together, and then checking that it's a commitment to 0. Right, adding commitments together, checking that sum is commitment to 0. Okay, so there is a little bit in there that is not entirely true, which is that in Monero, when a miner is doing this, they're adding commitments for transactions that you aren't actually spending to, right, the fake ones. And so the way you make it so that they all add up to 0 is weird, complicated math that I don't fully understand, that basically you make your output commitments in such a way that they cancel out the fake input commitments, but that the values in them are still, you choose the secrets on your output commitments so that they cancel out the values on the input commitments that aren't actually yours, which I don't get how that's possible, but apparently it is, and it's in the readings, I think. It's in the readings for Ring CT, which is using all of this stuff together. So you have a bunch of unspent confidential transactions, which I guess we never put in the slides for that. Whoops. So confidential transactions are transactions where all of the input and output transactions are these kinds of additive commitments, so that they can all be added together. So you have a bunch of unspent transactions that are yours, that you have, you know what their value is, and you know what the secret value is, and you have the private key that allows you to sign for them, right? And then you use a bunch of confidential transactions from other people who you don't have the private key for, but you know the public key, and you create a set of confidential transactions that are your outputs, and you construct their secret values in such a way that when you add together the commitments, it all adds up to 0. And then you create a traceable ring signature on this whole transaction so that a miner can check the traceable ring signature has not been used before. I can't connect this to a signature that already exists, so this isn't a double spend. It does match one of the private keys on the inputs, and adding up all the commitments, it ends up being a commitment to 0 somehow. And so yeah, that's right, the validator can check the signature. So yeah, all of that is a very, I think, confusing overview of all of it. And if you're interested specifically in Monero, there is a lot in the readings about the actual cryptography behind all of that makes all of that actually work and is less hand-wavy than what I've said. And yeah. So, assuming that all of that works and pretending that we all understand that, like, okay, how good is Monero though, right? Like, you have these commitments, you have public signing and, you know, ring signatures and all of that. So, okay, you don't have masternodes, you don't have to send your CoinJoin transaction to someone to facilitate it anymore. You just do it all yourself. That's nice. But the anonymity set is still pretty small, right? Because you have to select who the other public unspent transactions are that you're going to use. And you're not going to be able to select 1,000 of them. You're going to select, you know, 3 or 4 maybe. You can do multiple steps on your own, right? You can just keep running this. You can keep creating new outputs and then respending them back to yourself and create more anonymity for yourself. You still have the problem, though, that, like we said earlier, if I create a transaction using other people's outputs and then they spend those outputs in a way that de-anonymizes themselves, right? Like you can choose, or you could choose, not to include any fake transactions in your transaction. If you just do it directly, then there's no ambiguity about where your input went to an output, and that removes ambiguity from my transaction. And so this is, or was at least, a very big problem, because it's up to the client software to pick which other transactions you will use when you create your transactions. And up until September 2017, very recently, it wasn't mandatory for you to use ring signature or ring CT transactions, for you to mix in a bunch of other people's transactions. And basically a lot of people, I think there was actually, like, one of the popular clients, the default was no anonymity whatsoever, which meant if anyone used your transactions in their anonymity, you actually didn't add anything to their anonymity, which meant that it was possible to de-anonymize them based on you not sort of contributing to the anonymity. And so, yeah, many transactions before 2017 can be completely de-anonymized, which leads us to a paper called Monero Link, which came out, I think it was in the summer, and yeah, 62% of transactions before 2017 can be de-anonymized. And not just can, but like are.
Wouldn't that be obvious?
Yeah, but it's like, and that's the thing, right? Everyone knew that this was a problem, like they could see it, but no one had actually like done the research and then like built a tool that allows you to like look at all the transactions. And so someone did that, and they did all the data analysis, and they found that like not just is this possible, but like yes, it's possible, and these are the results. And so right, they use a lot of transactions have no mix-ins, and in the vast majority of transactions with mix-ins, the one that is the real transaction is the one that is the most recently created, because people were just running through multiple hops. And so if you create a transaction, then you take that output and make a new one, and you keep going. All of the mix-ins are going to be old transactions that no one is spending, and the newest one is going to be the real one that you just made. And so you can just follow right through. And yeah, Monero is not this vulnerable anymore. I want to make that clear that like it was very vulnerable, and someone did an analysis and found a lot of problems with it, but most of this has been fixed. Yeah.
When was this done?
This was done over the summer, I believe. I don't know when like the work was done. The data is everything from, I think it's actually up to like January 30th of 2017, but the like report on all of this was released over the summer, I think.
Do the creators of Monero, like, did they identify this as an issue when they created Monero? Like,
I don't know, not like when they created it. They've been aware that this kind of thing has been an issue, and that's why they've like mostly fixed it, right? By the time this like paper and this tool and all of it came out, most of this stuff had already been fixed. And then in September, they finished one of the last pieces of it, which is making it mandatory to use ring CT transactions for everything, which goes a long way to really fixing all of it. But it's just everything before 2017, they weren't confidential transactions, so you could see the amounts. It wasn't mandatory to do mix-ins, and so a lot of people didn't. And you had this problem that, like, if other people aren't being anonymous, that de-anonymizes you.
And so how many years of transactions was that? When did it actually?
I think it's like, I think 2013, 14. So it's like a couple of years worth of like, yeah. And the problem with all this, I think I took out there was another bit in here that was like, the takeaway from this is that like, no matter how anonymous we think one of these things is now, the data exists forever, right? Like the transaction graph, the data, all of it's going to be there forever. even if it is anonymous now, it might not be in the future, right? And so, and analysis tools are getting better over time rather than worse. And so we do have to consider that, like, even if I can prove that, like, when we get to Zcash, even if we can say Zcash is really anonymous and really great, it doesn't mean that, like, we won't break it somewhere in the future. And then, yeah, all that history gets de-anonymized. But yeah, on Monero Link, it's mostly been fixed. They talk about this in the paper, but there is still work to be done, because even if you make, anonymous transactions mandatory so that everyone is mixing in other transactions and every transaction has mix-ins and it's, really anonymous, you still have the problem that by default, the newest transaction in any set is almost always going to be the real one, that, like, most times if you're going through multiple hops, you're going to be going quickly through each hop, and so the other transactions that you include are going to be much older than the one you're spending. And so there's work that is still being done and needs to be done on client software to make sure that you select which, fake transactions you're including, so that it's not so easy to just say, well, in every step, the newest one is the real one. And that's still a problem, and they're working on that, and they've sort of fixed some of it. Yeah.
So I understand, like, so double spend is kind of solved now by all of these, but, like, is this taint attack and all sort of related attacks, is this, like, the new major challenge? Tracing relating transactions.
I don't know if I'd say it's this is the thing with blockchain, right? Like, there's so many different things going on in the space that this is, like, the stuff that, for this context, yeah, this is where the work is being done. It's like, okay, we have these systems that we think add anonymity, but now we're going back and we're looking through them and seeing how much anonymity do they actually add. And we're finding that it's not as much as we hoped. And so, yeah, there's room for improvement. We have to keep working on it and keep improving it. And, the problem with it, of course, is that every time we improve the analysis, we de-anonymize a bunch of people in the past who thought their transactions were secure. But this stuff is very experimental, and so that's sort of going to happen. But, I think it's interesting anyway, even if, as it turns out, it's not as secure as we were hoping. All right, so that basically covers Monero. That it, most of this stuff is solved, and so it is pretty secure now. It's not perfectly secure, and there may still be attacks, especially if you're running through multiple hops and you're going through each hop very quickly. So I guess if you're going to use Monero and you're going to, like, go through multiple transactions to try to wash your coins, take like 10 minutes between each transaction, so that your transaction is a little bit older when it goes into the next one. I don't know if that actually adds anything, but that's what occurred to me to try to do. So anyway, Zcash. Yeah, go ahead.
Quick question. Relative to being a centralized
Yeah.
approach or a decentralized approach, all these thus far have been pretty much centralized, correct?
Well, no. Dash attempts to be... Dash is still pretty centralized because of the masternodes, but the idea is that anyone can run one and you're going through multiple of them. Monero is totally decentralized. You don't have to rely on anyone else to help you build the transaction. You just have to do a good job of selecting what other transactions to use on your own. So Monero is very much, like, decentralized in that way, but you still are relying on the other members of the network to not de-anonymize themselves, I guess. Does that answer your question?
Could you forward if these are somewhat time sensitive relative to the transaction chain, I guess you could say?
Yeah, somewhat.
Could you go forward in time?
I don't know what you mean.
Well, if you scramble to put in enough mass to where it becomes confusing, if you were able to decoy with,
I sort of get what you mean.
Future timestamps?
Yeah.
Yeah.
So that you never know if you're in a future mode or a historical mode, other than if you put a true timestamp on it.
I don't know that would solve the timing problems, because I think what they're actually talking about is not actual time, but, like, which block the transaction came from. That, like, if you get a transaction in one block and you spend it in the next one, it's probably real that, like, that, the person receiving it is also the person spending it. It probably isn't some other person spending a fake transaction from the previous block. And so I don't know that you could really manipulate that with timestamps.
So liquidity is the key. If you can hold for a little bit.
Right. If you can put in some time between when you're doing all these things. Right. Yeah. Yeah. That would probably help. But the question is always, how do you make the wallet software do this automatically? Because people want to be able to say, like, I've received some Monero, I want to click wash, and it's clean. And it's like, well, you can't do that right now. You have to like manually send a transaction to another address, then wait, then send a transaction to another address, and just like go through this. And that's not what people expect when you say we have an anonymous currency, which is closer to Zcash, which we don't have as much about the cryptography of Zcash as we did about Monero, because one, I didn't have as much time to go through Zcash, and two, the cryptography is a lot messier with Zcash. So, in particular, we have ZK snarks, which are a zero-knowledge, succinct, non-interactive argument of knowledge, which, I mean, it's basically magic, but the idea is that it allows you to prove that you are spending a transaction that you own, and basically nothing else about that transaction other than that it wasn't already spent. And so this gives you that if I'm creating a transaction on Zcash, it's like, okay, this output, what are the possible inputs for that transaction? And it's like, well, every other transaction that's already in the blockchain. Like, okay, that's a pretty big anonymity set, right? Like, I make a transaction, I spend some money, where did that money come from? It came from Zcash. I think that's about as good as you can do with any of this. The problems with it are basically that it's really cryptographically like expensive, right? The computation to do this, you need gigabytes of memory, and it takes a long time. And like on my laptop, it would probably just kill it because the thing only has like 3 gigs of memory. But it's experimental cryptography. Like this is really cutting edge cryptography that's only existed for, well, I guess the cryptography, some of it has existed for a while, but like the application of like using ZK snarks to do, anonymous transactions has only existed for like 3 years. And so, they're working on efficiency improvements, which I guess we took that slide out. So basically you have a sender, a receiver, an amount, and you're doing the same UTXO model, but everything's basically encrypted, right? Like the UTXOs they're the Pedersen commitment schemes from earlier, basically, with more complicated stuff in them. You write a ZK snark proof, basically, that the thing I'm spending is valid, hasn't been spent, that I know the private key that goes with it, and that the outputs I'm spending it to are also valid. And you don't reveal any information beyond the fact that all of those things are valid, and that you know the information associated with all of those things, but you don't reveal any of that information to anyone else. So this is sort of an overview of what ZK snark actually means. But I feel like that overview doesn't actually tell you that much about what they mean, because a lot of those words are sort of just words, right? Like it really just comes down to the cryptography works in such a way that you can do really complicated proofs of really complicated things without revealing any information about the things. And it's a cop-out, but we couldn't think of a way to actually, the way I went through the Monero cryptography, I feel like was all right, but I don't understand that stuff. I definitely don't understand Zcash cryptography enough to really go through it even at that level, even hand-waving and saying like, well, this is not correct, but it's close enough. There is stuff in the readings, and I would definitely recommend people read it, and I definitely want to read it because I think Zcash is probably like the best potential right now in all of this because, as we said back here, right, maximal anonymity set, right? When you create a Zcash transaction, the possible inputs for that transaction are every other transaction on Zcash. And so you really can't do better than that, right? Like it's as good as you can possibly get. It's just that it's really expensive and it's not well understood and it's, really messy and there's a lot of work to be done on making it efficient. And there actually is some work being done on making it efficient that Zcash is doing. Yeah.
So who came up with this? Where was it conceived?
So Zcash is sort of descended from a thing called the Zero Coin project, which was originally trying to put this stuff on Bitcoin, which I think basically didn't happen because they realized that it would be, one, really hard to put on Bitcoin, and two, the Bitcoin governance process is a mess, and so it wasn't worth it to try to do that. It was developed by, I know one of the people who developed it because he's a professor here, Alessandro Chiesa, I believe is how you pronounce it, and some other people whose names I don't know. Basically, really smart cryptographers came up with a protocol that would allow you to do fully anonymous transactions on Bitcoin, and then they adapted it into being its own process. But the thing they made, ZeroCoin, could actually be applied to any UTXO model-based currency. It doesn't have to be Zcash. It's just that they managed to bring together enough people to make it into its own cryptocurrency because it looked like it wasn't going to happen on Bitcoin. But more work is being done on the cryptography to make it more efficient, and they've got a thing called JubJub, which I don't know why they named it that. Something to do with Lewis Carroll, I think. Yeah. Right. But so they're making improvements, and from what I've heard, those improvements are very promising. They're not yet implemented, and when they do implement it, it'll have to be a hard fork because this is like the foundation of the cryptocurrency. You can't change this stuff without a hard fork, which is going to be somewhat disruptive. But there's a thing in the reading guide that links to the stuff about sapling is like the general term for the next like iteration of Zcash, and it goes through all of the different efficiency improvements they're making, and it looks like they're really good because they got the memory costs down from 3 gigabytes to something like 40 megabytes, which is totally reasonable. And so it seems like if that stuff works, if the math is good, if it's secure, then essentially Zcash would be by default anonymous. It works, it's efficient, you can run it on a smartphone, hopefully, and that would give an actual, fully anonymous cryptocurrency, which I think right now we don't really have. Yeah.
So, the main person who worked on Zcash is actually Matthew Green.
Oh, right, Matthew Green, yeah.
And so I think the reason you can't, going back to the timestamp, the reason you can't put future timestamps is because of game theory attack that involves when you set attached to basically when the network as a whole has to be on a certain time.
Right.
Time of the network. And there's a game theory that you start increasing your own reward by putting in slightly different, slightly future timestamps. It's really prominent in Bitcoin. It's not so much done, so much in Monero, but in Bitcoin, there's a reason you don't mess with the actual timestamps of the hash blocks or the transaction blocks that those transactions. You can look it up. It's quite common in the Bitcoin community because the Bitcoin community is expanded to such a point that you have adversarial attackers in the network that are actually trying it out. Monero hasn't reached the community where you have that level of adversarial attackers.
Right. All right. Yep. Good.
Your thoughts on the trusted ceremony and the fact being 20% of the transactions are actually shielded?
Right. We didn't get into either of those. Trusted ceremony is like an unfortunate thing. Basically, to create ZK snarks, you need a piece of data that is publicly. Basically, you need like a public-private key pair that everyone uses the public key, and hopefully the private key is deleted and no one has access to it. Because if it isn't deleted and someone has access to it, then they can create new coins themselves. And so Zcash, they did this thing called the ceremony, where they got a bunch of like somewhat trusted people in the community to come together and to run a multi-party protocol to generate, this public value that everyone needs, and then delete the pieces of the private value so that it could never be constructed. We think. But it's right. It's like, well, you got to trust that they actually did the ceremony, that they didn't, smoke and mirrors it, and you got to trust that like no one hacked all of their computers at the same time to get the private data out. And it's kind of unfortunate that that is a necessary part of ZK snarks. Ideally, you could make it so that it isn't. I personally would hope that you could come up with better multi-party computation protocols that would allow a larger set of people to participate. Because if you had 1,000 people participating, like the idea is as long as at least one person destroys their private piece of the data, then it can't be reconstructed. But the problem is if you do like 1,000-person multi-party computation, if one person like fails or drops out, the whole thing falls apart and you have to start over. And it's like a multi-hour long process. And so it's like, it's just not efficient to do it with a large group of people. And so they instead did it with a small group of like people in the crypto space who trusted each other. But for people who don't trust them, it's a little bit like, I don't know, maybe you guys are like lying and you just kept it and you're just issuing Zcash to yourself. But I personally don't think they would do that because they already get like 10% of the block reward or something.
Wasn't there some like blog post ZK Snarks versus ZK Starks or something?
Right, ZK Starks is the other thing that I also don't know as much about as I would like to, and I need to read about that. And I should have put something in the reading list about that.
Something to do with the whole trusted ceremony and being
okay.
I forget. It was a couple months ago.
I'm not familiar with ZK Starks as much as I need to be. Yeah, I should look into that. The other thing you said, though, was the only 20% are shielded, which is unfortunate, right? That, like, yeah, the thing I said about, oh, where did the transaction come from? Somewhere on Zcash. It's like, well, it's somewhere in the 20%, because you're only anonymous if you choose to be, which I do think it should be by default, but I can see why they would have made it not by default, because it's so computationally intensive to do shielded transactions that they wanted the currency to exist and allow people to have transactions even if they weren't trying to be anonymous. I would hope that in the future Zcash would make it mandatory to use shielded transactions for everything, because I think that would just be better. There's also a whole other thing about like selection bias with anonymity, that if you are being private and there is some cost to being private, then you're only doing it because you want privacy for some reason, and that makes you more of a target. Whereas if everyone has privacy, then that's better for everyone, that like you don't have to sort of proactively choose to have privacy, and therefore you're not sort of liable for that choice, right? That like someone can't be like, what do you have to hide? You know, if everyone is doing it by default. So I do think that would be better, and I hope that they do that in the future.
I mean, that's an issue with Tor right now.
It is a big issue with Tor, right?
Tor.
If you use Tor, it's like, why are you using
I
Tor?
can hack you,
Yeah.
right?
Well, hopefully not, but anyway. So I hope you guys enjoyed the presentation.
Thank you.
Thank you.